What's going on, everybody? This is Mr. Diamond, recording from the safety of my home, as you can probably see behind me. And we're going to be doing the notes for Section 2 of Chapter 2 of Advanced Chemistry. This is going to be describing solutions. Now, last time we talked about a little bit about the solution process, how we actually get to our different types of solutions. We talked about the heat of solution. We talked about this whole expanding of the solute, expanding of the solvent. And then we also talked about the three ways you can increase the speed at which a solution breaks down. Again, none of these will actually make something that isn't going to dissolve. The thing either will dissolve in water or whatever you're dealing with, or it won't. But the amount can change, and that's actually one of the things we're going to start talking about this time. So there's a lot of different ways or a lot of different types of mixtures that we talked about. We talked about the homogeneous, the heterogeneous, all of that kind of stuff. But there's also multiple different types of solutions. And the way we describe these solutions depends on how much solute, which remember, that's the thing that is dissolved within a given solvent. So that's the thing that does the dissolving. I also mentioned last time, I believe, you can tell because of where I'm recording that these weren't recorded at the same time. But I believe last time I talked about how, like, for example, the air that's in front of us right now is an example of a solution. Nitrogen would be the solvent because it's the predominant component of our atmosphere, and then solutes would be everything else that's in it. But an example of like Kool-Aid, water would be the solvent, and solute would be the actual Kool-Aid powder and the sugar you dissolve in it. We are going to represent the types of solutions, though, using one of the most southern things that hopefully a lot of people feel like they know a little bit about, and that is sweet tea. Now, let's say you have a pitcher like this, and some of you may have a pitcher that looks exactly like this, although I guess the handle would probably look a little different. I've never seen a handle like that. Usually it's a little plastic one. But let's say you have a big pitcher of iced tea, and you add 1/4 of a cup of sugar to it. Have you added enough sugar? Well, most likely not. You could probably dissolve more sugar into the tea. And if it's real Southern sweet tea, it should be super, super, super sweet to an almost disgusting level. So no, probably haven't. You could dissolve more sugar into that tea. And so when you have a solution that more solute could be added to a given solvent, we call that an unsaturated solution. It is not saturated. Now, we use that term saturated in organic chemistry to refer to hydrogens. This is a different way of using it. It is the same word, and that is unfortunate. But it still is the same basic idea. An unsaturated compound could have had more hydrogens attached to it, so an unsaturated solution can have more solute added to it. So let's say then we add more sugar to our tea. We're going to go all the way up to, let's say, a cup of sugar for one little half-gallon pitcher of tea. You're also confident that you can't dissolve more sugar into the tea. Nothing else will dissolve. If you put it in there, it would just do that gross sink to the bottom thing, and it would just like have all these grains in the texture whenever you try to drink it, and it wouldn't be very good. You have gotten all of the sugar that you can into the tea. At this point, that tea would be called saturated. So again, saturated meant had all the hydrogens in organic chemistry. Here it meant means has all of the solute that could possibly be dissolved in it. And then finally, we here in the South would not be happy with just having all of the sugar. We would want even more sugar. We want more than can actually be dissolved in there. So what we do is we heat up the tea to a really, really hot temperature, and then we dump in a whole bunch of sugar when it's really, really hot. And then as it cools down, that sugar stays dissolved, even though if you've ever tried to make tea sweeter when it's cold, you know that you can't just stir in sugar, even though you know that the tea could get sweeter. And that is because the heat allows more of the stuff to be dissolved into it. So if you have more added to something than can usually be dissolved in it at a given temperature, we call that a super saturated solution. It is beyond what it should be able to contain at a given level. And usually you have to do that by getting a little creative with the heating something up to a really, really high temperature, adding all of the stuff, and then cooling it back down after you've done that. So those are our three types of solutions. Unsaturated, a solution that contains less than the maximum amount that could be theoretically dissolved at a given temperature. So now we're adding that little caveat there. It's at a given temperature. That's why we are able to make supersaturated solutions, because if it was more than could be dissolved, well, that just wouldn't make scientific sense. But it's more than can be dissolved at a given temperature, and that actually makes sense, because if we make something really hot, it can have more stuff dissolved in it. Again, this is why I also specified at the beginning of the video that it won't make something that can't dissolve able to dissolve. For example, if you put a chunk of styrofoam, making the water hot isn't going to make the styrofoam dissolve. The styrofoam will not dissolve in water, but sugar will dissolve in water at any given temperature. It's just the amount will change based on the temperature. So if you have below the maximum, that's unsaturated. If you have at the maximum, that's saturated. And if you have above the maximum, that is super saturated. Now, these are a lot more common than you may think. Usually you need to do some tricky things to get a supersaturated solution, but it can result in some cool things like the sodium acetate reaction. I'll probably show this in class. I'm going to try to I think we have some sodium acetate back at the lab. So whenever we get back in person, I'll hopefully be able to show you this demonstration. But what we are going to care about mostly is graphically representing saturation and determining how much can be dissolved in a given solution. So this is what these graphs will look like. They are called solubility curves. So down here on the bottom, we have temperature, ranging from 0 to 100, which makes sense because we're dealing with water. And you may be thinking, well, why does that make sense? Well, if you think about it, what temperature in Celsius does water freeze? 0. So how much can you dissolve in frozen water? Well, usually not a lot of solids. You just kind of pour it on top of the ice and it won't do much. And then the temperature over here goes up to 100, which is boiling point. And if it's water vapor, obviously you're not going to usually be dissolving a lot of solids in there. I say usually. You can, but that's more complicated than we're going to get to in this class. Over here, we have solubility, and that's in grams of salt in 100 grams of water. Make sure you read the questions, and you make sure you read the graph before you kind of start going into some of these problems, because I think all the graphs I've shown you, because all the graphs you can find online assume 100 grams, and it assumes 100 grams of water. But it may not show water over here, and this may not be 100 grams. It might be in 50 grams or 200 grams. Or the question might ask you how much could be dissolved in 200 grams, and if that's the case, you'd have to double whatever number you are getting from the graph over here. So we have a whole bunch of different colored lines. Obviously, on your worksheets, they usually won't be colored because it'll be black and white. Although if you're doing them digitally, they might be colored, depending on the source I got them from. So this is the graphical representation. Each of these lines represents the saturation point at a given temperature. So for NaCl, for example, right here, at 10 degrees Celsius, NaCl can get about 35 grams of salt in 100 grams of water. And if you heat that up all the way to about boiling point, you can get about 5 more grams of NaCl. It stays pretty constant throughout there. But some of these, you'll notice, go up a crazy high amount, and there's even one of them down here that actually gets lower as you heat it up. That's a little bit weird. So going back to salt, though, for our easy example, so this whole line would be the saturation point. Anything below this line would be unsaturated solutions. It would have less than the maximum amount of that given temperature. And anything above that line would be a supersaturated solution. So for example, if you heated water up to about 90 to 100 degrees Celsius, you dissolved 40 grams of salt into it, or into 100 grams of water, and then you cooled it down to almost freezing. You cooled it down to 10 degrees, not even almost freezing, just say 10 degrees. Would get it to having 40 grams of salt, even though normally it should only be having 35 grams of salt, and that would be a supersaturated solution. So everything above whatever line you're looking at, supersaturated, everything below, unsaturated, and exactly the line is a saturated solution. So this is me describing all of this stuff, and this is me describing all that stuff. Awesome. Now, there's one other thing you can determine here, and it's because, like I pointed out here, this one swoops down while most of the rest of them swoop up. You can actually determine if a reaction is endothermic or exothermic based on the shape of the curve. If the substance loses solubility, as in it lowers as you increase the temperature, that is an exothermic reaction. And if you're wondering why that is, we will talk about that once we get to Le Chatelier's principle. I don't remember if that's this chapter or if that's next chapter. But there is an actual explanation for that, and we will get to that. But if you see a slope down, that means it is an exothermic reaction. So adding heat to it doesn't help because the reaction itself produces heat. So that heating it is not going to allow more of it to be dissolved. If the substance gains solubility as you increase temperature, so if it goes up, then it is an endothermic. I'm sorry, my thing's blocking up. An endothermic reaction. So all of these would be endothermic. This one would be the only exothermic. NaCl is not very endothermic. It's pretty small window. The band doesn't change that much. But this one is greatly affected by it. These one is greatly affected by it. All the ones that slope upwards are kind of very, very affected by temperature. Okay, so this is what a question on the worksheet will actually look like. So first, check the graph. It is in temperature, degrees Celsius, grams of solute per 100 grams of water. Okay, so we know we're dealing with 100 grams of water, and we know it's water that we're dealing with. First question is how much KClO3 would normally be dissolved in 100 grams of 30 degrees Celsius water. First, we need to find KClO3. KClO3 is right here. And then it wants to know in 30 degrees Celsius, and it wants to know how much should be in 100 grams of water. Well, the graph is straight up telling us it's how many grams in 100 grams of water, which means right here, I would say that is about 10 grams of KClO3. And this will be a window that I will accept on test questions and on worksheets. I will accept multiple different kind of like, usually within plus or minus 2 of each of these answers, unless it's very obviously on the line. Then I'll be a little bit more strict. Okay, next question. Let's say you have dissolved 100 grams of ammonium chloride. So I need to find ammonium chloride, NH4Cl. It's right here, NH4Cl. In 200 milliliters of 40 degrees Celsius water. What type of solution is it? So first, let's check. It's 40 degrees Celsius. At 40 degrees Celsius, that's about 45 grams in 100 grams of water. Now, it says it's in 100 grams of water, but the question says 200 milliliters of water, and you might be thinking, well, is that like a typo or is that a mistake? And no, it's not, because you need to remember, we talked about this very briefly in organic chemistry, we talked about this a little bit in chemistry, I believe, as well, that water has a density of 1 gram per 1 milliliter, which means this 100 grams of water is the same thing as 100 milliliters of water. So 200 mils means the same thing as 200 grams. You can use those interchangeably, and I'll sometimes use them interchangeably in questions. Anyway, back to what we actually care about. So 40 degrees up here, that's about 45 grams in 100 grams of water, or 45 grams in 100 milliliters of water. So in 200 milliliters, that would mean that you could fit 90 milliliters or 90 grams of ammonium chloride in 200 grams. And since 100 grams is above that 90 point, that would put it somewhere up here, which would be a supersaturated solution. The other way you could do this is you could convert this and say, well, if it's having 100 and 200 milliliters, that's the same as having like 50 grams in 100 milliliters. You can basically just divide the ratio out so that way you have 100 as your number that you're using here, so you can compare it to the chart. In this case, divide that by 2, you get 100. Divide that by 2, you get 50. Come over here to NH4Cl. 40 degrees Celsius, 50 is above the line, so that would be a supersaturated solution. And then finally, it says, which two elements appear to be the most exothermic when dissolving? So most exothermic means we're looking for the ones that are sloping downwards. And in this case, there are 2 of them. I'm blocking one of them a little bit, so you can't see exactly what the name of it is, but it is Ce2SO4 and that's this thing right here because it's slowly sloping down. And then NH3 is sloping a lot more strongly right here. Now, I kind of worded it a little bit on the last section, or a couple of slides ago, that it's a bigger slope is more exothermic. If that's how you interpreted that, that is not how I want you to interpret it. A bigger slope does not guarantee that something is more endothermic or more exothermic. At least I'm not 100% sure of that, so don't quote me on that. In this case, though, you're just looking for slopes mean exothermic, sloping downwards. Slopes upward mean endothermic. All right, I believe that takes us up to concentrations. So that's going to be a second part of this video. That's where we're going to start getting into a whole bunch of math. There's going to be a whole bunch of calculations and problems for you to solve related to those. In the meantime, though, that's it for this video. This is Mr. Diamond. I hope you're all staying warm and have a good day. Enjoying the snow a little bit. My cat is sleeping in the window right behind my computer monitor, so I think they've enjoyed us being home for a while. So have a good rest of your day, everybody. Send me an email if you have any questions, and I'll see you guys in the next video.